Hello students, welcome to the next session, lecture 11 of power electronics. So we are starting module 2 and our first topic of discussion is principles of operation of an SCR. So in this module, as I said, I had mentioned earlier, module 2 will be mainly discussing in detail about the SCR device, power semiconductor device. All right. So in this session, mainly we will start with the principal operation of an SCR. So by the end of the session, you will be able to identify the SCR symbol, describe basic operation of an SCR, explain how SCR works, and describe the characteristic curve of an SCR. All right. So, the silicon control rectifier, abbreviated as SCR, is a three-terminal semiconductor switching device, which is probably the most popular compared to the diode or the transistors. All right. So, it was invented in 1957 exactly by Bell Telephone Laboratories, where they published first paper with this PNPN device, where it was used to perform various functions such as rectification, inversion, and regulation of power flow. So the SCR is been assumed with very importance in electronics because it can be produced in versions to handle very high current, say up to several thousands of amperes, and voltages up to 1 kilovolts. Okay, so if you look at the images I have shown here, they can be of different packages, as you can see from the image, and they also come with different names. Okay, some call it as thyristors, some call it as thyroid transistors, etc. And SCR is a popular name. So it is, in fact, it is a unidirectional power switch. Okay, and mainly it is extensively used for used in applications where switching from AC to DC or vice versa, for rectifying AC to control DC, or converting DC into AC, etc. Okay, so mainly it is used in rectification process, and it is used as a switch. So in this chapter, we will examine various characteristics of silicon control rectifier and their increasing applications in power electronic circuits. Right. So. Before I start, let me give you one information. Why the name silicon control rectifier? Why not germanium control rectifier? See, because mainly it is made of silicon, all right? Why not germanium? Because when the device made from, say, silicon or germanium, irrespective of that, a device in off state, when it is not conducting, there will be some small leakage current, isn't it? So this small leakage current in off state, in the silicon type of material, it is very less compared to germanium. Okay, that's why popularly silicon is used. All right, so it gets this name silicon control rectifier, and as I mentioned just now, it is mainly used in rectification application process, application circuits. So that's why the name rectifier. And since it can control the power that is fed to the load, or you are able to control the rectification process using this device, that's why the name silicon control rectifier. All right, and we will go in detail when we discuss the circuits. All right, so this silicon controlled rectifier is a semiconductor device that acts as a true electronic switch. As I mentioned, it can change alternating current into direct current, and at the same time it can control the amount of power fed to the load. All right. So it actually combines the features of both a rectifier and a transistor. All right. And also just for your information, this silicon control rectifier is a solid state equivalent of a thyratron. What is thyratron? It's a type of gas filled tube used as a high power electrical switch and control rectification. So it is initially it was the uh, it was a device used for high power electrical switch applications. Okay, so since it has a transistor, that is function of transistor, and it resembles the application of thyratron, the name is a combination of thyratron and transistor, that is thyristor. Okay, it's also called as thyristor. Now it's a three-terminal device. As I mentioned, the terminals are, as you can see, anode, cathode, and gate, and its main uses are switching and amplification. All right. So if we look at the basic structure of SCR, then it is, if you say if you add a PN junction to a junction transistor, if you add a PN junction to the say a PNP or NPN transistor, generally it is PNP transistor, then what you get is a three junction four layer device. If you add a PN junction to a transistor, then you get three junction four layer device, that is PNPN, okay, which is called a silicon control rectifier. So if you observe the construction, and generally it is this is a symbol, as you can see, it looks exactly like a diode because it has the PN junction added to the transistor. It looks exactly like a diode, but with extra terminal, that is gate, right? So it's a four layer device. Now you can imagine also the internal structure to be like two transistor connected back to back, that is PNP transistor and NPN transistor. If you are connecting it back to back, then you can imagine the internal structure of the SCR. All right. Now observe here, this is your first transistor PNP. The emitter of this transistor is P type, base of N, and collector P. All right. So the base of the first transistor is connected to the collector of the second transistor, that is NPN transistor. So both the N type materials are connected here, and the base is P, which is connected to the P type collector of the first transistor, and N type emitter of the second transistor is your cathode. So you have the anode terminal, which is nothing but the emitter of the first transistor, the cathode terminal, which is the emitter of the second transistor, and if you are connecting the collector and the base of the two transistors, that is P type material of the two transistors, then that is your gate terminal, right? So just imagine two transistors connected back to back. Okay, so that is the internal structure exactly. So it is clear here, you are adding a PN. It is essentially an ordinary rectifier that because it has a PN junction and the junction transistor combine to form PNPN device. All right, and the terminals are one from the outer P type called as anode, and the second from the outer N type, that is the cathode, and the third from the base of the transistor section, the second, that is called the gate terminal. So in normal operating condition, SCR, always anode is held at a higher potential compared to the cathode. Alright. So let's see how the SCR works. So how does SCR works? So as I just mentioned, generally the load is connected in series with anode, and always anode is kept at higher potential than the cathode. So the elementary circuit for obtaining the static VI characteristics of a thyristor or a SCR is shown here. The anode and cathode are connected to the main source through the load, and the gate and cathode are fed from another source, EG. So this is your gate drive circuit. So anode and cathode are connected to the external source or the main source, all right, via the load, right? So this circuit will help us to get the static VI characteristics of an SCR, all right? So, to understand the working of SCR, we can look at two different conditions. One is when gate is kept open, and the second is when gate is positive with respect to cathode. Okay. So, first condition of the working of the SCR when you are keeping gate open. Alright. And second, when you are applying potential here with respect to gate and cathode. Alright. Let's see what happens. So when gate is open, what happens? When gate is open, the circuit is shown here, as you can observe that. So there is no voltage applied to the gate terminal, right? So observe the junctions there, and you are applying voltage across anode and cathode. This is our anode terminal and this is our cathode terminal and this is our gate terminal, all right? So this V is nothing but say VAK. You are applying voltage across anode and cathode. Okay, and just recall, always anode will be held at higher potential compared to cathode, and this is your load. So what happens? So when there is no voltage applied to the gate at this condition, observe the junctions there. J1 is forward biased, J3 is forward biased, but junction J2 is reverse biased. Alright. So it is similar to the situation where your transistor is open with the base open. That is NPN transistor is with the base open. That is the condition, right? What happens? Now J2 is reverse bias. What happens? There is no current flowing through the RL, isn't it? So this SCR is in off condition or it is cut-off condition. It is in cut-off condition. What happens if you gradually increase the voltage that you have applied across anode and cathode? Okay, so if you're gradually increasing, there is a stage when the J2 junction breaks down. Okay, that means as you go on increasing the voltage between anode and cathode, at one stage J2 breaks down and there is heavy current flowing through the device, or we can say the SCR conducts. Okay, so that voltage we call it as breakover voltage. Okay, the voltage at which observe here the gate is still open here, all right, there is no voltage applied at the gate terminal, but you are gradually increasing the voltage across anode and cathode. So at one point there is SCR starts conducting, that is there is a flow of current taking place. Okay, so that voltage we call it as breakover voltage. Okay, now what happens when gate is positive with respect to cathode? All right, observe the condition. The SCR is made to conduct heavily at small applied voltage at the gate. Okay, that is a small positive potential is applied at the gate terminal. Now look at it, what happens? Now the junction J3 is forward biased, J2 is reverse biased. Okay, now when you are applying this small potential, very small potential, so there is a small current flowing through, so it can be a pulse. So what happens? The electrons from the N-type material start moving across J3 towards left. The electrons from this area start moving towards left, whereas holes from the P-type material starts moving towards right. So consequently what happens? Electrons from the J3, junction J3 are attracted towards junction J2 and there is a gate current that starts flowing. Consequently, what happens? So as soon as the electrons are available at junction J2, then the J2 breaks down and the SCR starts conducting heavily. Okay, so once SCR starts conducting heavily, then this gate terminal loses the control. What does it mean? If it loses the control means even if you remove this current, if you remove this small potential what you are applying, even then the device continues to conduct. Okay, so let me go back to the circuit of two transistors. Okay, I'll explain here again the concept here. Now what is happening if you are, say you are applying a small potential at the gate terminal, so there is small current here. So this current, okay, it is this current that is at the base of this transistor. So what happens? This will create charges, right? So there is charges at the collector. Now observe, the collector is connected to the base of the transistor 1. So all the charges that are getting accumulated are getting flooded at the base of this transistor 1. So what happens? Now again there is charges getting collected or the current flow that is taking place at the collector. Now again in turn it is connected to the base of this transistor. So what is happening? There is a continuous tremendous flow of charge carriers, or you can say there is continuous increase of current flow happening. Okay, so even now at this stage, even now if you remove the gate signal, then that doesn't make any difference to the device, and there is continuous increase of current taking place. That is the significance of SCR. So for SCR to turn it on, you need very small signal, say small current, okay, say in terms of pulse. So just a pulse if you apply at the gate, that will trigger the charge carriers in the device, and there is continuous increase in the current flow that is taking place. So even then if you remove the signal at the gate terminal, the device will continue to be in the on state. That is the meaning what we just now discussed. Okay, so that is about a gate being positive with respect to cathode. Now to understand the working again, as I mentioned, SCR has three basic states. First is the forward blocking mode or the off state, where the device blocks the forward current, okay, similar to what we had in the diode. Second is the forward conduction mode or the on state, where the device, that is SCR, is into conduction. And third is the reverse blocking mode or off state, where SCR blocks the current in the reverse biased diode situation, similar to diode. Okay, so this is the VI characteristics of SCR. Okay, typically, if you observe the reverse blocking region or the reverse blocking state, so it looks similar to the diode. Okay, when you apply reverse voltage, reverse means what here? You are making cathode positive with respect to anode. Okay, that is when you say the switch is open or the device is not conducting, right? So what is the condition of the SCR here? SCR is in reverse bias condition. Okay, so in the reverse bias condition, what happens? The thyristor exhibits a blocking characteristic similar to the diode. Alright. So in this condition, what happens? The J1 and J3 junctions are reverse biased, and the middle junction J2 will be forward biased. So because of this, a small leakage current will be flowing in the across the junction J2. Okay, small leakage current in terms of milliamps. Alright. So if you go on increasing this reverse voltage, okay, if you apply increase the reverse voltage, then at one stage there is a breakdown taking place, or we call it as avalanche condition happening. Okay, what is avalanche condition? It is nothing but because of this reverse voltage applied, and we know that there is a small minority charge carriers present, right? So due to which there is electric current multiplication taking place, and this will make the charge carriers in the transition region to get accelerated, isn't it? So they will get accelerated in such a way that they acquire the energy where they get tremendous mobility, or the energy that will create mobility, which will cause free electron pore pairs, right? Because they start bombarding with each other, right? So which in turn will cause increase in the charge carriers. Okay, so in this avalanche condition, there is a tremendous or sudden increase in the current. All right, I hope you recall the avalanche condition. Okay, so the voltage at which this avalanche condition take place is your reverse breakdown voltage. All right, so but if you look at the characteristics, it is slightly different from that of the diode. It is slightly different. Let us go in detail one by one. So forward blocking state is one where the voltage across the device is high, and there is a small current. Okay, we call it as leakage current, right? And this is the state where SCR is in off condition. Okay, so in this off condition or the forward blocking state, as you observe, there is small leakage current because of the minority charge carriers. Next is the transition state. Now what happens? As you observe, if you go on increasing the applied voltage, you are applying voltage across anode and cathode, right? So as long as this voltage applied across anode and cathode, it is less than the breakover voltage, right? Then SCR remains in the blocking state. So that is where you can see small leakage current. But as this VAK increases the VBO, breakover voltage, then what happens? Suddenly there is increase in the anode current. Okay, and observe that the voltage across SCR, voltage across the device suddenly decreases. Suddenly decreases. Remember the ideal characteristics. Yeah, when the device is switched on, the voltage across it will be minimum and current will be maximum, right? So voltage decreases and the current will suddenly start increasing. So this is the transition state where the current starts increasing and voltage immediately becomes less. I'll repeat, when you are increasing VAK, when this the voltage applied across anode and cathode, it is crossing the breakover voltage. That is, when there is a breakover voltage, that is where the junction J2 breaks down, right? So when this breakover voltage is crossed, there that instant the voltage becomes less and current starts increasing. So that is the transition state. Okay, it takes place in a short time. All right, so after that what happens? The device is conducting, or it is in on state conduction mode. We call it as conduction mode, where the device is conducting. That means there is a maximum current flowing through the device. So the voltage across the device will be low. Okay, the voltage across the device will be low. All right, and the current, the anode current, what you are talking about, will be in as large as 2000 amperes. Remember, initially when I started the session, I told you the SCR applications, it can handle very high current and voltages up to 1 kilovolts, right? So the average current what you can measure, the anode current can be as high as 2000 amperes in the on condition, and the voltage drop will be few volts, right? So this is the on condition, and the reverse blocking region we have already discussed. Now there you can observe some other parameters here, IG1, IG2, IG3. Okay, what is happening here? Observe that. Now initially what we discussed, all these characteristics were said when the gate was open. Okay, now what if gate, there was some signal applied at the gate terminal. Now if you apply some gate terminal, then this transition what we just now discussed, this transition can take place earlier. Okay, okay, so by applying gate signal you can make the device conduct faster. That is the meaning. All right, now see, IG, this, say the breakover with minimum gate signal, say gate current is 0, Ig is equal to 0, then as usual what we just discussed just now, so when the VAK crosses VBO, breakover voltage, then device starts conducting. Okay, now if I apply say some small gate signal with gate current Ig1, then this transition or where the device is turning to on condition can happen faster. Okay, now if I increase this magnitude of this gate current, okay, then even further it can be made to turn on faster, and this is Ig3. Now as you can observe, Ig3 is greater than Ig2, greater than Ig1. So based on the gate signal or triggering what you are giving at the gate terminal, you can make the device come to the on condition faster. That is what is shown here in these characteristics. Okay. Now there are other parameters IL and IH. IL is nothing but latching current. Okay. Now when the device is turned on, okay, now there is some anode current, isn't it? So the minimum anode current that is required to keep the device in the on condition is my latching current. I'll explain. Okay. Latching current is nothing but the minimum anode current that is required to keep the device in on state. That means what? Say you need some minimum charge carriers or the current to flow, right? So the minimum current that is required to keep the device in the on state. That is when there is like continuous multiplication of the charges happening and the increase of current taking place, right? If you recall the two transistor construction what I just now explained. Okay, so the minimum, that is the start of the current that is required to keep the device in the on state, is my latching current. Okay, and holding current is 1. So this is a minimum current. So after this, if you are reducing the gate signal, so when you reduce the gate signal, the anode current also will naturally decrease, isn't it? So the minimum anode current at which the device turns off is the holding current. All right. Okay, let me put it in another way. Now I just now said with the gate triggering signal I can make the device conduct. When I say device is conducting means there is some current flowing through, right? That is my anode current. All right. Now according to these characteristics, if I have to summarize, wrap up, now based on the gate triggering signal I can make the device conduct faster, right? Okay. Then when this gate terminal or the gate triggering signal is removed, I just told you the device continues to be in on state. Okay. Now what about turning off? So that's why if you recall, we had mentioned in second session, I think, SCR is uh, SCR is a device where turn on is controlled and turn off is uncontrolled, right? So to turn on, you can give this gate signal, which is controlled parameter. Okay. While to turn off, Even when you remove the gate signal, what did I say? The device continues to be in on condition. So turn off is very difficult. One thing is what you can reduce the gate signal, or you can reduce the voltage in such a way that the anode current also drops. Okay, so anode current becomes minimum and then the device turns off. Or another method is you have to use some external circuitry where you will reduce this anode current. Okay, now coming back to this holding current is the minimum anode current that is required, okay, below which the device will turn off. Okay, so this is the definitions of latching current and holding current. Latching current is a minimum anode current required to maintain the thyristor in the on state. Okay, immediately after it is turned on and the gate signal is removed. All right, and holding current is a minimum anode current to maintain the SCR in the on state, or below which the SCR will be turned off. All right. Okay. So that is about the principal operation of SCR. So mainly, as I mentioned, it is mainly used in rectification. That it is used in regulated power supplies, motor speed controls, and battery chargers, etc. Okay, the applications of SCR. So that's all for today's class. We'll wrap up and we'll continue with the further topics, that is two transistor model of SCR. We'll go in detail with the construction part and all, with equations and uh, so on. So see you in the next session. Thank you.